Board. And there we go. All right, so back to the AEJ slide deck. Let's see. Anything you guys want to talk about before we get started with new material? So we did a decent number of things last time, right? So we kind of talked about the overall AEJ process. We talked about we basically introduced a new problem to do, right? So we're doing one sample problem here. We're doing kind of an algorithmic problem, right? So when I talk about AEJ, right, when I talk about these 3 steps, you can kind of apply them to whatever you want, right? All sorts of problems. For us, because we're in 222, the example I'm choosing is an algorithmic one. Some of the stuff I'm actually showing you guys is probably more advanced than you typically would see in the first semester data structure and algorithms course. Some of the stuff they typically save for an algorithms design course, right? So for you guys, a lot of things we've been doing is basically learning a bunch of different existing algorithms. And it's like, well, if I want to, have this existing algorithm, this existing sorting algorithm, right, merge sort, whatever, someone else built it, so they've already shown that it works and it's good, right? They've already done all that work. And so in a lot of traditional courses, they don't actually talk about any of this stuff here because the notion is that you're not building things from scratch. And so we're actually, kind of building a little thing from scratch to give you guys experience with that, right? With what does it take to basically, put forward, right, an idea for an algorithm that is, new and novel, so that it kind of survives, being out there, in the wild with everybody looking at it and evaluating it, right? So this is a little bit advanced, right, for the course we're in, but I think it's good stuff to start seeing. The example we're seeing here is pretty, I think, straightforward. It's straightforward and then also it's reasonably well defined, right? So obviously things can be much, much worse. If I have a chance, I might actually tab over and show you guys some other ADJ style questions for other classes that I teach. But my problems can be a lot more complicated, right? So in a sense, ADJ is a little bit of overkill for this style question, but it's still good stuff and it's a nice way to practice. So yeah, as a kind of a reminder, right? Last time what we were doing is we were saying, okay, let's solve the problem, right, of implementing a little algorithm to basically update the contents of a priority queue. So we had our problem statement over here. This is what we were working on last time. This thing right here. So this is still pretty well defined, right? This isn't, as ill-defined as, your boss saying just make the customer happy, right? Or this is broken, fix it. This isn't too bad, right? This is pretty straightforward. That's because we need kind of a starting place. All right. So talked last time. I know we went through some of these quickly. If you guys haven't seen it already, there's already a couple of PDFs basically that have this complete, worked problem. There's extras of it inside of the slides, so you can see I have my little screenshot there. Those are coming from a longer thing, right? So if you go, there's I think a 3-page, PQ update PDF, right, which shows these different little portions, has everything worked. That's on there. There's also a document called K, which we'll talk about later on today. But just be aware those are on Canvas, so you can take a look at them. Let me know if you see any bugs in them, right? And actually for these slides as well, if you guys see anything weird or doesn't make sense or there's typos or whatever, please let me know. All this stuff right is brand new. I haven't used it before. And I just kind of, created everything over the past couple of weeks. So, if you see anything weird, let me know and then I can fix it right now. That I really do appreciate. So yeah. All right. So again, right, do reference, right, eventually, right, there's the stuff on Canvas, which has kind of the distilled answer that we're working towards here. Okay. So kind of the slides that we left off last time is this one. So we're right now, right, in the analysis portion, right? And as the first step of analysis, we want to define things, right? So we need to know what's what. If I'm not clear sort of on, what I'm doing or why I'm doing it or what I have available to help me, well, then I'm just going to get kind of bogged down and not be able to make progress towards an actual solution. I need to have a firm foundation to work from, right? We want to be what they call well-founded, right? So I'm using some of the terminology here that you might encounter basically in math or philosophy, right? So they'll talk about, something being well-founded or something being sound. I think a lot of times, right, people hear those terms, they immediately jump to like, to mathy stuff. And they think like, oh, when the professor gave me this Boolean formula and they asked me what was sound, that's what it's about. For us, that's not really what soundness or being well-founded is about. For us, what it is about being able to produce solutions that are correct and that are right. I mean, that's it, right? We want to be right. And we want to be right all the time. We don't want to be guessing, right? And a lot of times when people design things, they are in a sense guessing because they haven't really tied together everything in a way that kind of follows logically, right? And so that's why we talk about soundness here. It's like, okay, whenever as I build my solution, do the parts follow from what I did earlier, right? Does everything line up? Because if it lines up, well, then the conclusion I reach is going to be a valid conclusion, right? And that's what I want. I want something that is correct. All right, so our final step here in definitions, right? Having gone through the stuff in the previous slide, which is really all about defining what it is what is a priority queue. We're actually going to define here what a solution looks like, right? So you can almost think of this as kind of being a fill in the blank template, right? So no matter what the solution may be to our problem, right, of updating a node in a priority queue's heap, every answer should be able to look like this, right? And the key aspects we're kind of capturing here are the input and the output, right? And I know this was harped to you guys before. Right? Probably you took 110, 205, you're like input, output, and then you forgot about it for a little while, right? So maybe it wasn't really necessarily mentioned in other classes. That's something you need to know, right? And here I've kind of loosely defined it. Sometimes right, people will be very, very specific on like, what do you expect in? What do I expect out? Because that's sort of your rules, right? Your rules for your input give you what is valid to assume, what can your algorithm rely on, and your output is sort of like the contract, if you would, right, with the outside world, right? I promise to do this, right? I promise to build this output. Input and output aren't necessarily just things like, oh, I take in a number, and oh, I put out a number. It's about what can I assume about that, right? So a negative number goes in, but whatever comes out has to be a positive number, right? It specifies some constraints on what your input and your output looks like. That's what we want to specify there, right? And so anyways, the idea here, right, is we're basically saying this is how every possible solution to this problem could or should look, right? And it kind of becomes a fill in the blank for all this stuff over here, right? That gets filled in. Now, the top part over here, right, this is, I think I called it model last time. Basically, that's our representation, right? A representation or model for, what this thing changes, right? It's not getting all of the inputs as parameters. Really, it has some state, right? That it's going to update, right, depending on what I tell it to do. So this is so that's kind of your secondary part, right? So your algorithm has input, output, and then there's some general state that you transform. For some people in their styles, what they like to do is they like to put all this stuff over as parameters. I'm not too keen on that myself. I mean, we're building stuff to run in Java, right? Java is an object-oriented language. You have state that your thing operates over. I think it's better kind of to still remember that knowledge, right? To still remember that you have kind of some stuff you can operate over. So yeah. All right. So that's going to be our basic format of our solution. So the next step, right, which is kind of a big one, right, for analysis, is basically the idea of metrics, right? So I want to be able to say at the end of the day that my implementation of this algorithm is sufficient, that it's an answer, right? Imagine it's you looking at a rubric and wanting to make sure that you get full marks on the homework, right? Well, the only way you can do that is if you have a rubric to begin with. So we're effectively building our own rubric. We're defining what it means to be a good solution, right? So for us, that basically means look at the question prompt and trying to figure out what is important. And there are kind of two different things to unpack, right? So we have kind of so we have this metric over here, and this is actually M2, right? We're being asked, right, to define an efficient algorithm, right? So just look at the prompt. Efficient is one of the characteristics of our solution, right? The thing we're building, right, is the algorithm, right? We're building this, right? And one of the properties we want for it is it's efficient, right? And then the second thing, right, is we want to do this. Update the priority of an entry inside of a priority queue, right? This is the second part, right? So this, right, is basically a Boolean requirement, right? I need to be able to do this. Versus the other one is it's just efficient, right? And the problem is I'm not told how efficient, right? And we talked about that last time, and when I asked you guys, what was unclear here, what was underspecified, you guys were like, oh, it's efficient, right? So that's one of the problems because we don't really know how fast this thing is supposed to be. And we also so we don't know how fast it's supposed to be, but at the same time we also realize that there's a reason it's there, right? Because if I don't put the word efficient there, somebody could have an algorithm that takes a million years to run, and it would still be a valid answer to this problem, right? So we need to have something in there to at least tell us, oh, it needs to be reasonably fast. The thing is, though, we're not really being that specific here. We're not saying that the algorithm needs to run in like big O of n squared time, right? Sometimes you guys have seen that, right? Like in the homeworks, they'll say, okay, run, create an algorithm that runs in this amount of time, right? Here we're not given that much guidance. We're just told it needs to be, efficient, whatever that means. Well, both of these things, basically, we need to make them more specific so we actually know what we're asked to do. Hence, we have M1 and M2 up on the screen. So M1, right, and I'll read this to you guys, right? This somehow is me, look at the question, kind of, trying to understand it from everything we've done in the past, putting it into words, right? There is a little bit of a flavor here, I think, of me making assumptions, reasonable assumptions of what to do, or what is meant here. So I'll read this, right, and maybe we'll see if you guys, have any problems with this. For me, I think M1 is okay. There's a particular part in M2 that I'm not a fan of, but we'll read through these and maybe we have some discussion if we can. So for M1, our first metric, right, is the ability of the algorithm to process a heap ordered array with at most one node, which violates the heap rule, and produce a heap sorted array with no violations of the maximum heap rule, right? So we're talking about the input, we're talking about the output, right? So a heap, right, is the input with one violation, or at most one violation of that rule. And then we want to get something that is, no violations right at the end, right? That is a proper heap. And then the last thing there, which kind of comes out of the blue a little bit, is the array must contain a complete tree at all times, okay? So my question to you guys is, how do you guys feel this captures this part over here? Does it seem okay, or is there issues? Are we adding anything or skipping anything relative to what the question prompt is saying? How do you guys feel about M1? Maybe I'll just do, let's see, can I do a little? I'm also thinking about using the polls instead of Zoom, but the problem is I like doing them on the fly, so usually I just write up here. What do you guys think? Is M1, does it miss anything from the prompt, or does it add anything to the prompt? My chat window vanished again. What do you guys think? Maybe I'll sketch over here real quick. Let's say, adds, skips. Okay, what do you guys think? Those are the three categories. Or if you guys want, you can write on my screen. What do you guys think? Is this M1 definition? Does it add stuff in the prompt that's not there? Does it skip stuff that's not there in the prompt? Or does it seem okay to go? What do you guys think? My chat window for Zoom just completely disappeared. Oh, there it is. Okay. Okay, so one person says okay. Anybody else want to agree, disagree? Okay, so still just have, okay, so we have a couple of votes for okay. Okay, so several people are saying this sounds good. So my question to you guys then is, where does this part down here come from? So I don't say complete tree anywhere up in the prompt. Why is this here? Where does that come from? Can anybody want to speak up either on voice chat or you can type in text chat? Why is that last part then there, right? So if you say it's okay, right, that implies that it's not me adding information. So why is that last part there? Why do we need it?
Because your client is finicky?
Because your client is finicky? Well, but see, and then we're adding a little bit of information because we don't know, like, we would have to basically say, okay, I'm worried that the client might not like this, so I have to add this there. So so that I would say we're adding a little bit of information. Let's see, any other ideas we got for Bill?
Well, that is one of the key definitions or key components of the definition of a heap, including that is more just saying, here, we're going to stick to this definition of a heap.
Right. So here, right, we have basically, so we're saying we're going to use a heap, a priority queue, right? And so we have basically this notion of a PQ, which then goes to a heap, right? And we had to talk about what does it mean for something to be a heap? Well, a heap by itself just means the rule, but then because we know we're also looking at a specific implementation of it, we know that basically we have to have this as a heap or array, right? I have to have an array that stores all these things with those little formulas. And in there, basically what I do is I encode it as being complete, right? And so if I want my update algorithm to work with any of the other functions, methods within my priority queue class, then I need to maintain a complete tree, right? I can't disagree with how the thing is stored. Otherwise, right, basically my update won't work with insert and won't work with delmax, right? So it needs to line up with what's already there. So that's where our second constraint comes from. Right, so comes from that over there. All right. Let's see. So I think we're okay for that one. Let's look at M2, the efficiency of the algorithm. For a cost metric, we will use the number of lines run as a measure of computational time used for a particular design. How do you guys feel about this? Let's say it's, maybe I'll clear the arrows up there. So good, bad. What do you guys think? And how do I clear? This thing is not cooperating. Clear, okay. Clear all, there we go. Okay. So what do you guys think? The main part here, I think that's kind of in doubt, or I would wonder about, is for a cost metric, we'll use number of lines. How do you guys feel about that? Do we have any alternatives? Is there anything else I could use other than lines, other than number of lines run? Do I have any other choices?
Big O?
Okay, so big O would be a way that we basically, like, that's what we would talk about. We would say, okay, the number of lines run is big O of n, or big O of n big O of O of 1, right? Big O is going to be how we talk about them, right? So we will use big O here. But then big O, right, can be used basically to measure different things. So here, the thing that we would be measuring with it would be number of lines run. Are there any other alternatives though for things, other things that I could run, or other things other things I could count?
The goal is to update the priority. So I guess you're going to have to do some comparisons to find
Okay.
the element you're looking for. So you could check the number of comparisons you have.
Okay, so number of comparisons. Right, that would be an alternative metric. I kind of feel that number of comparisons would be better than number of lines of code. The reason that I pick number of lines of code is because actually it makes the analysis harder. If I pick number of comparisons, it's too easy, and so I didn't do it. So comparisons, right? Or if we can do comparisons, right, we could probably also do exchanges as well. Exchanges, we'll just say that's an E there. Okay. So yeah. So this is where we're going to go. These are our two metrics. This is what we'll need to show to prove that our answer is a good answer for this problem. Okay, so just a summary real quick. So things, right, we've done, right, is we've tried to understand the problem, right? So we did things like just reading through the prompt, right? Trying to see what's ambiguous, what's not. You know, trying to, you know, basically do a little bit of an example, which is pretty straightforward for us here, right? We just had this one little tree, like, oh, we swapped it and we moved it up and things are good to go. It's pretty straightforward, right? For other problems, it'll be a lot trickier, and you may need to spend hours doing examples to get the intuition for how to solve it. So number 2 here, right? You know, sound technical context, right? Basically means we have our good foundations, right? So we have our definitions of what it means to be a priority key, what it means to be a heap. And then we have, you know, the notion of the metrics for how do I measure what's a good solution or not. So now basically, now I know what I can do, right? So I know, well, in problem solving kind of lingo, they'd say, you know, I know the actions I can take, and then I can do and then I have the ability to check to see whether I'm at my goal, right? Am I done, right? That's the way they talk about those things. If you look at well, if you look at problem solving, you know, theory, or you look at AI, right, which is kind of related. You said, okay, we have, you know, we know our we know where we began, but we know our options, and we know how to look when we're done, right? That's what we've completed here in analysis, right? So now we have this, right? Then we can get on to a design. Now here, right, the problem is relatively straightforward. So we're going to probably use everything that we talked about. A lot of times, though, right, as a reminder, the stuff you see in analysis won't necessarily, you know, show up again, right, later on in design, right? Maybe that we do more work than we need to, and that's fine, because at this point we don't know what a good answer looks like, right? We don't even know what an answer is, period, right? Much less a good one. Okay, so now kind of on to the next part, which is updating a priority queue. So we need to do the actual design for this, right? The actual creation of the algorithm for this. So the first thing I want to talk about is actually not specific to the algorithm itself. It's just kind of algorithms in general, which is pseudocode. So these slides here are so they're here, and then to me honestly they're a little bit weird. I kind of always assumed that in previous classes you guys were shown what pseudocode is, and then what I found though, when I go and teach class, so when I teach more advanced classes, like for example my operating systems class, I ask for pseudocode, and then people don't know what to give me. which I find is strange, right? Some people will basically just be like, give me a couple of words and say, oh, okay, it's cool. That's not really pseudocode. Pseudocode is basically something meant to strive for clarity, right? So either people will give me things that are basically programs that are completely, I could just run them, right? They'll be like, oh, it's better than pseudocode, you can run it, which I suppose is true from one aspect. Or they'll give me things right there, just sentences, and it's like, it doesn't make any sense, right? So for you guys, right, I'm explicitly telling you, what pseudocode should look like. And it basically is going to look pretty much like a programming language. Just going to be a little bit more generic. The key thing here is that when people write pseudocode, is it really is focusing on clarity, right? Not making the algorithm happy. And also, it's not making the algorithm happy, and it's also not meant to hide things, right? So another thing I've seen in my other class is I'll ask people for pseudocode, and there'll be these like magical methods, right? That just do everything just happens, right, in them, right? So they may give you a little program, right, and all of a sudden, right, it makes a call to something that's not written down, like, oh, it's pseudocode, it's fine, I don't need to write everything. But then basically it kind of takes care of their whole problem all in one go. So I guess so I have the examples here I'll talk through. So imagine, right, you have a piece of pseudocode, right? So I'll jump forward for a second, right? So pseudocode is on the right-hand side. It looks a lot like the Java, right? It's a little cleaner. It looks a lot like the Java. In our pseudocode, right, somewhere over here, right, you do things like you can potentially, call a different function, right? So, when you do that, right, when you're writing pseudocode, right, kind of a way to explain your algorithm, well, people do different things. It's okay to do things like, for example, say, oh, you have, it's 2 points, so I take the distance between them. If your pseudocode says, it open-endedly says take the distance between 2 points, that's fine, because, well, distance itself is well defined, right? So if I have 2 points, I know exactly the formula to use. Versus, for example, one that people have been using in a wrong way, again, in my other class, is they said, okay, I'm doing pseudocode, but then the function that my pseudocode calls is going to use something called, has deviation. And it's actually an image comparison function, right? So it takes in 2 images, it compares them, and returns a Boolean, true or false. Is there a difference between the 2 images? Okay. This thing over here, right? You can kind of see the definition there, right? Just this function here called has deviation that compares 2 images. People in my other class did that, and the problem with that is I don't know how you're comparing images. So, how are they different? Are the colors different? Are the pixels different? Is looking for motion? How different do the images need to be, right? How do I take care of things like, I have images, right, that maybe there's just a little bit of noise in them, right? Maybe I'm comparing JPG images and they just have a little bit of compression in them where they don't quite match up pixel per pixel, right? So then if you mention that in your code, like, oh, I have pseudocode that does this, well, that's not really a fair thing to say, because now that you've introduced something basically that's not well defined, right? That would be an issue, right? So again, right, focus of pseudocode, right, is just, clarity, right? Making sure you talking about exactly what you're doing, right? It doesn't necessarily have to be, like a program, right? And in fact, we kind of want to avoid, writing programs. We just want to focus on expressing our ideas, right? So I have some rules on the right-hand side. So if I ask you guys for pseudocode, right, this is what you should follow, right? So, use basically block indent, right? So rather than doing the semicolons, right, which can be confusing, just use your indent to show, different blocks of code, right? No semicolons are dumb. Use words instead of and, or, and not, right? Use loops at kind of a more generic form, right? For, start to end. Use complete type names, avoid plus, avoid minus, right? Just try to make your code a little bit clearer, right? So these things I would ask as rules for you guys to follow. Other than that, right, it's a little bit open-ended. As some quick examples, right, I have 2 algorithms here, right? So this is actually insert and swim from the priority queue, right? So left side is the Java that we talked about in the previous module. And the right side is me just rewriting it to look more like pseudocode, right? So you can see that I've just cleaned it up a little bit, right? So you can see bracers are gone, right? There's the indent there. I've added a little semicolon at the end to show this is the beginning of a function. And I have my code there, right? And most of it looks pretty similar, right? You can see that I've just done a couple things to clear it up, right? So I took out the pre-increment and I put it on its own line, right? Here I actually added another variable, so it was more clear that k divided by 2 was a parent, right? Again, I'm focusing just always on clarity, right? So yeah, so there's a few things, right, that are kind of different from the pseudocode to the normal code, right? This one over here, right, it's not as compact as the real one, right? It may also not be as efficient as the real one, but again, the idea is I'm just focusing on the communication of ideas, right? So I'm changing things, right, just in a way that they are, a little bit more clear to the reader. All right. Questions, comments, concerns, complaints, critiques. Otherwise, I'm going to see if I have one more example of pseudocode to show you guys. Okay. Let me show you guys a little bit more. Yeah, we can leave that open. Okay, so hopefully you guys can see that. So you should see a PDF overlaid on the screen right now. If you don't, let me know. Okay. So this is a PDF, right, of some sample pseudocode for a problem from my other class, right? So this is, like I said, this is some of this, right? There's some stuff happening in parallel, basically, with my operations class. This is more pseudocode, right? And you can see what I hopefully consider to be, you know, a more reasonable pseudocode here, right? So this is a larger example, right? It actually uses stuff you guys haven't seen yet. So there's more stuff here on threading, and you can notice, right, that things are defined, right? So it's like, well, I mentioned, you know, has deviation over here, so that means I do need to define it later on, right? That type of thing. Focus again, right, is on clarity, right? This is actually, so this is from operating systems. Operating systems is actually a class where you use C. So you can notice here we're not really using pointers, right? So those of you who are taking 240, right, know that you have to use that star and ampersand all over the place. We're omitting that from pseudocode, right? We're just trying to make it as simple as we can. So yeah, so this is just kind of another example, right, of what pseudocode might look like. This is pseudocode for an algorithm that is supposed to basically process some image feeds and detect if there's an unexpected object there. So yeah, just another example for you guys what pseudocode should look like. Textbooks will also have other versions of pseudocode, right? People basically, everybody has their own format for it. For me, you can make me happy by just making sure that you're clear in whatever you write and you don't introduce any ambiguities. All right. So yeah, so that's pseudocode. So we'll be using that. Okay, one other tool to pick up before we talk about you know, our actual problem statement. So here is basically the idea of what I call K. Now, don't worry about this too much right now, because I've basically given it to you guys in the example. Somehow what K is so I use it basically to represent what you know, right? What is valid knowledge that you have, right? And so K stands for knowledge. The idea of being is that rather than kind of just use what we know, or more importantly, what we think we know, we should write everything down, right? So when we did all those definitions, right? So we did definitions for, you know, a binary tree, a complete binary tree, right? A heap, right? Write those down, right? Write those down and put it into a document that maintains them for you, right? So rather than just being like, oh, I'm going to jump straight to talking about heap ordered arrays inside of my algorithm, write down those definitions in a separate document and maintain those, right? The idea is that we want to be all on the same page. So usually what happens is that I've asked you guys to write one of these, is I can either, you know, tell you to come up with, you know, a separate document that has your definitions ahead of time, or have a class-wide one, right? So for this class, this is what this means, right? You know, so I might define, you know, a heap is, you know, all heaps are maximum heaps, right? I could do something like that, right? There's basically just this idea that I want to keep track of what is it that are my foundations, right? What is the knowledge that I build on? Because a lot of time, right, people have definitions that don't match up. So yeah, so just, you can be aware of that letter there, right, of K. If we need it for the homework, I'll explain a little bit more in detail. For now, I just think of it as a way to talk about or group all my base definitions that I'm going to be working on top of. Okay. All right. So now we need to get into design. So let's see what we can do. So we have a reasonable, you know, idea of our problem, right? So we want to update the priority queue, right? So we want to basically solve that thing on there on the bottom where I have the 14 kind of out of order, and then I have the corrected version on the right, right? So I know that's what's going to do what I want to do. Can I break into pieces, right? That's my first question, right? So decomposition is a pretty, well, I mean, it's a standard technique, right? So whenever you're faced with a problem that you don't see an immediate solution for, make it simpler, right? Always make your life easier, right? Sometimes people want to do things that somehow, you know, make it more complicated. Don't do that. Make it simpler. And decomposition gets you that, right? Decomposition basically says, look at a problem, try to break into subproblems, right? It's almost maybe the same. It almost has the flavor, right, of recursion or divide and conquer, where it's like, well, we have some large problem and we want to break into smaller pieces, right? With the assumption that smaller pieces are going to be simpler to solve, and if we have solutions to the smaller problems, we can put them together in a way that, you know, gives you an answer to the whole thing. So yeah, so that's what we want to do here. So do you guys have any ideas for how can we break this down? What are the pieces we could potentially break this into? So we have our overall problem here we want to solve, right? So our job is to implement this thing over here. Do you guys have can you guys think of any way to basically break our problem into little smaller pieces other than fix a priority queue or update a priority queue? What do you guys think? Is there any sub pieces we could maybe try to break it into? What do you guys think? What do I see inside of the overall problem of update a priority queue and correct an entry?
Maybe we can say check for any. Well, first we would have to check for any errors and then identify the errors. So,
Okay, so
like with 14, of course, we have to go through the priority queue and understand that it has to have the top-down structure, aka one node. The parent node has to be greater than the child, and then check for that. And
okay.
then we say, okay, if we see something that doesn't look right, what should we do? Should we sink or swim it? And
Sorry.
then, yeah.
Okay, sounds good. Did somebody else have something to add? Sync. There you go. All right. So I think that was Devon. I don't know. I don't know his username, so I have no idea. It could be anybody.
Yeah, that was me. But my,
Okay.
my username, I can't change it because I can't see where I am. So,
I can change it. What do you? Maybe I can change it.
well, yeah.
Rename. Look at now we get to see if I can spell your name.
Uh-oh.
Wait. I don't think that's. I have it, but I think it's wrong. Okay. I renamed you, but I'm pretty sure I misspelled it.
No, you spelled it right. It's
Is that
just
right?
a capital V. Yeah.
It's a capital V. Okay.
Yeah.
I'm
Funny
surprised that
business
is right.
stuff.
I don't. Yeah. All right. So yeah. So a couple things there, right? First of all, we got to see if there even is a problem, and then where it is. Because the thing is that when I do this on paper, I just look at it. I'm like, oh, that's out of order. I know what to do. Your algorithm can't do that. Your algorithm has to do the nitty gritty of finding out where the issue is. And then once the issue is there, is found, then we do a sink or a swim on it, right? To kind of correct it. Okay. So to me, I think that kind of sounds like there are maybe two steps in here. Okay. Yeah. Just let me think. I think maybe I'll just answer that question in there for a second. So it says, is it always safe to decompose a problem? The answer is yes, right? So if you have something complicated, you can always, it's always going to be fair game for you to break it into pieces. And those pieces should always reassemble. If you want to, you can prove that answer to yourself. But that's you'll find if you do it, right? It's always fair game to break something down. And if you can break it down, it'll always reassemble. You don't lose soundness when you decompose something. You never do. And if you want, you can write a nice little mathematical proof on it. But I won't do that for you guys because that's a little bit more work than we need to do. All right. So I'm going to jump to basically the complete algorithm because that's not, because in a sense it's not really what we're talking about here, right? We have these other techniques. I'm assuming if I give you guys this at homework, you could program it up and you could solve it, right? So I'm not going to spend a ton of time to do the algorithm itself. We already kind of know the direction that we're going in, right? So that's pretty good. So yeah, so kind of I think what I had, it kind of lines up with what Devon said. So step one, right? Find target key / value. Step two, if needed, adjust the position at target key / value. Right. So these are, are things that we want to do. All right. So this is my proposed algorithm, and at this point, I have no idea if it's a good algorithm. Now I could implement this. I could run it. I could test it. But the problem is if you do it that way, you're only going to know that you're going to know that it works for the test case you choose. You don't know that it works in general, right? And usually that's what we want. We want a more thorough knowledge, right, of what it is that we've created, right? We want to be sure for sure that whatever it is you created is a good algorithm, right? So yeah. Real quick to walk through this before we start talking about it and try to justify that it's a little bit, good. Let's just talk about these lines for a second. So basically what we do, right, is you create a variable to store an index, right, so the target. Then we basically search the entire tree, starting at index 0, and try to figure out, where is the one we want to update, right? And so you can just kind of remember, right, this thing is a heap order array. That means there's an array somewhere looking like this, blah, like that, right? Start at 0, right? We basically are walking along that and looking at every index, which seems kind of bad, right? Because surely I can do it faster. But here we're saying that we have to have, right, this is a event loop here, right? That probably should be a little bit concerning. You're like, oh, there's got to be a faster way to do it, right? Because, normally priority queue operations are log n time. Surely there's a faster way to do this. But that's what we're doing right now, okay? So we search through it, try to find it. If we don't find it, right, we can just say, okay, hey, there's nobody even to update, so it must be fine, right? So then we can exit out. Otherwise, right, we basically need to check it, right? So we need to check to see whether it needs to go upwards or downwards. Now, if I think of, so basically if I picture a priority queue right now, I'm like, okay, I have this node I need to update. You can basically imagine that you have two choices, right? Either you can move it down or you can move it up, right? Even though there's two choices to move it down, it's not really it's not an doesn't really represent an extra choice, right? Because you need to move it in a way that, it satisfies the heap rules. You basically just have a Boolean choice. Do you go up or do you go down? And so over here, you basically have an if statement that says, okay, depending on that, either go up or go down, right? Either do a swim or do a sink, right? One of two things. And then we use our formulas so that we know we're kind of moving around the tree the appropriate way. So yeah, so that's our simple algorithm there, right? Find it, decide, and then rely on sink or swim, right? And that's something we mentioned earlier. It's like, well, I have things that can help me out already, so I just, let me just reuse them. Okay? So yeah, so that's our basic algorithm. All right, questions, comments, concerns, complaints, critiques. Otherwise, we'll go to justification, which is kind of the longer section. All right, so hopefully that means everybody's good. All right, so justification. So I'm going to show you guys kind of, I'm going to show you guys some proofs, okay? So when you took discrete math, I know you guys saw proofs, so it sounds like you guys spent a decent amount of time on them, right? And you probably did things like prove, for example, relationships between numbers, right? Or relationships between operators, right? You did things basically that were mathematical. Here we're going to do things a little bit differently. We're going to do proofs for properties and algorithms. So the first proof I want to talk about is what they call a proof of termination, right? So as it stands, right, and you can kind of suspend your belief for a second, I don't really know if this algorithm terminates. Now, I know that if you look at it, you can be like, oh yeah, sure, it does. But in principle, right, if somebody designs an algorithm, the first thing you need to know is, does it ever end? Because an algorithm that doesn't terminate is an algorithm that is worthless, because it doesn't always give us back an answer. So the first thing that people will actually try to prove about algorithms, right, so this is proving properties of algorithms, is prove that it terminates, right? So proof of termination asserts that for any valid input, your algorithm will always terminate in a finite amount of time, okay? The alternative, right, is you have like an infinite loop, infinite recursion, right? Not really a good thing to have. Generally, right, we start with a proof of termination for an algorithm's correctness as kind of a way to say, oh, at least it runs, right? It's the mathematical equivalent of pressing F5 and seeing if the thing even compiles, right? If you can't show it terminates, it doesn't even count. Now, the way we typically do that is by finding something we call a progress metric, right? So basically what we want to show is that there's a way to measure how much work your algorithm is doing, and showing that it's basically completing work, right? It's making progress until it gets down to nothing, right? There's basically nothing left to do. Maybe in there's a little bit of a flavor of recursion, right? We need to show that we're doing work and we're getting to the end, okay? So that's our goal. Some quick examples here at the end. So example one, right? So you can imagine you have some sort of an algorithm that maybe displays out the constants of the array, right? Maybe it's using something like a for loop. The way you'd prove that terminates, you say, okay, I have my algorithm that prints out this array. It starts at 0. The array ends at n. I move up one at a time, and I always increment. Therefore, over time, I will basically approach my goal of being n, and I'll exit out, right? Super simple. Another algorithm, right? So this is another example. So maybe you have an algorithm that finds a path from one place to the other, right? So maybe there's a path from, I don't know, from my house to campus, right? How do I show that works, right? Well, I basically need to show that I try all the different possible routes to campus, right? That every possible place between here and campus is reachable, right? that I check, right? That I don't repeat myself, that I don't go and loop an infinite number of times, right? I want to basically take a finite number of steps, right? And that I maybe don't visit any place twice, right? Then I would maybe be able to basically show that my algorithm for finding a path terminates, right? And there, basically, just I'll draw a little picture for you guys to make that a little bit clearer. As you can imagine, right, you have this kind of, well, they call it a graph, and we'll be talking about them in this class. You have basically this graph, right, of different routes you could take, right, to get to school. And you can basically just imagine, right, let's connect those two. That's like I'm starting over here, and I'm ending over here. Start terminal is what those letters stand for. And I want to basically show, right, that if my algorithm tries to find a path and I start to that terminal, it'll actually do it, right? It won't just break on me. So I need to basically show all these things for, like, to show, basically argue that I move along that graph, right? You can imagine those lines there, basically those are roads, and the circles are intersections, right? So I have different choices of ways I could go. And I would need to prove, right, that if I have my algorithm for finding my route to school, right, it doesn't just get stuck, right? I don't just go around the block a bunch of times and drive forever, right? It's a little bit of work to show, right? So if you want to, you can try proving that on your own once you get to the graph algorithms. But that's just kind of just another example, right? I want to show that an algorithm terminates, and the algorithm is pretty much not trivial. So yeah. All right, so this is our first goal, proof of termination. So we'll look at an example really quick. So this is the swim, right? So I'm actually going to talk about swim for a couple of examples, and then we'll jump to our algorithm. So proof of termination for swim. This again, right, is meant to be a very simple example, right? And so I have the code, right? The pseudocode just on the right hand side. And so I know you guys, right, already kind of know how swim works. So let's see. Looking at that code there for a second. Is there a good variable I could use to indicate the progress metric? If there is, I would say circle it on my screen. What could we use basically to keep track of how much progress, air quotes, we've made on our problem? What do you guys think? Like I said, feel free to circle on the slides. What variable in that pseudocode, right? So looking at this little chunk here, what could we use as a measure of how much work my swim algorithm has done? What could I use? Don't have that many choices. So I think a natural choice here to use for our way to measure progress is the value of k, right? So k is an index into our array, right? So you know that basically this thing over here, right, gets, kind of put into some sort of an array, right? We know that our heap is somewhere here, right? And if I do swim, I'm basically being told that there's a particular node that's out of order, right? So there's some kth node here. So let's say this is k over here, right? I am looking here in the array, right? And basically this k, right, is kind of defining how close I am to the end, right? Whether the end means the leaves or the end means the root, it's defining how close or how far I am, from the stopping position. So I would actually take k to be my progress metric, right? And that kind of works out because k comes in as a parameter. K is also checked. K is also manipulated. Okay, so we'll say that k is my progress metric. It's a measure of how many nodes I've seen or how many nodes I have still to deal with. And so in that case, right, basically I look at that, I'm like, okay, that's my progress metric. And then what's relevant to me is the fact that it, decreases, right? So k divided by 2 a whole bunch of times. And then also, right, I have that while loop there where I check k greater than 1, right? And so if k is constantly decreasing, eventually I'll get, 1 divided by 2, right? That'll become 0, because here you can see k is an integer. And then I will exit out of that loop, right? And so then I show that it always ends, right? So I'm starting at a certain point, I always get smaller until I get to nothing, and nothing is sufficient for me to break out a loop and terminate, right? And so you can see that written with words on the other side. All right, is this right side, Jacob?
Left side.
Okay, left side, Jacob. All right, left side, Jacob, what do you got?
So I was wondering if k is still a good good tracking metric because it's getting divided by 2 each time? Does that matter, or is it still?
Yeah, well, actually, that's valuable to us because we know it's getting smaller, and we want to have basically a metric that decreases all the time.
Okay.
Because that's how I show that it basically hits my base case of this termination condition, which is k greater than 1 from the while loop. So yeah, it is here what I want. It is.
Okay.
All right. So quick questions for you guys. Would this still? Well, okay. Okay. So would this still work if I had the termination condition be k not equal to 0, right? So rather than k greater than 1, right? So that's my condition in the while loop. Would it still work if that instead was replaced with k not equal to 1, right? So this part here, if it was replaced with this over here, would this still work? What do you guys think? Yay or nay?
It would still work, but you couldn't do a double like you have in
Okay. So k will. So if I do k not equal 0, it'll still work because at least because like I have to basically I have to pass through there, right? I know I'm gonna see it at some point. Where you get into issues is if you skip over the end of this termination condition, right? So if it's 0, it'll still work out here. Usually people do the inequality thing though, because they want to basically like say, oh, if I put in a negative number by mistake, it'll still exit out, right? That type of thing. And you said something that you said double won't work. Why doesn't double work? What is the problem there? Anybody?
The reason double, well, in that instance, double wouldn't work because if you divide by 2, it'll just get infinitely smaller and just approach 0, but never equal 0. And so
Exactly. So this relies on the fact that eventually we do integer division. We get whole numbers. We get eventually a 0, right? If we do doubles, then it'll give us weird round off errors, and it may actually basically not hit that base case that we need in order to terminate. So yeah, fortunately everything's straightforward, so we know for sure it'll run. Okay, so yeah, so that's a simple proof of termination for swim. Now we'll do the one for the actual algorithm we propose, right? So this one actually is in a sense simpler, because basically what you say is, so like this part over here, right? And you can see the text here on the left-hand side, so you can read it yourself. But basically what we say is, okay, every line basically just runs once, right? So I start over here, I run through that, okay? Then I go through here. That's a looping structure, but I'm running from 0 to n-1, which is the size of the tree. The size of the tree has to be finite. It can't be infinite. So this is basically me running a finite number of lines. I don't have a good as good a metric for progress as I did for the previous algorithm. There I had k. Right now instead I have to basically use lines of code, which is not the best, but it is what it is. So that though we can basically infer that runs a fixed number of times, right? Because the array has a fixed size. This runs exactly once. This over here either runs or it doesn't run. And this over here, right? This basically just runs once, right? So all these things in here except the loop run once, and the loop we know runs a finite amount of time. So this thing should terminate. It terminates if and only if these two also always terminate, right? Those are my little unknowns. In my proof, I say that we assume it. We actually just did prove one of them though, so we know that's okay. So yeah, so this one is not too bad, right? Because it's a pretty simple algorithm. Let's see. So for us, we're not gonna if you go look at the write-up for this, right? The actual answer, it doesn't have the proof of termination in there. The reason for that is basically that we focus on correctness instead. The thing is that for correctness, if your algorithm is correct, right, it always gives you the right answer. That also implies that it is, that it terminates, right? That it does get to the end, because there's no way it can give you the right answer all the time if at some point it doesn't give you an answer, right? So yeah. Generally, the proof of termination is what you see as a first step, right? So if you're not sure if your algorithm even runs, right, you do a proof of termination to show that it at least terminates, right? Again, this is simple stuff. For more complicated algorithms, you're going to be like, oh, I don't know if it ends or not, right? And then this will be some more kind of important work. For now, I think it's maybe a little bit obvious. All right, so next thing I want to introduce is proof of correctness. So a proof of correctness basically shows the algorithm does what it's supposed to do, right? So I have the output that looks this way, right? Given that the input looks like this, I always get an output that looks like that, right? So I always get, the maximum value in this input array when I put in my, my binary search algorithm, right? Something like that. usually this is what we care about, kind of number one, right? Is does the algorithm do the correct thing, right? If it doesn't, back to the drawing board. The second thing we care about, right, is it fast enough? That's sort of an orthogonal question, right? So we have capability to do things, and we also have the efficiency in which we do that, right? Those are different things. For now, right, we just want to say, can we do things the right way? And generally, the way you do this is by looking at an algorithm and try to understand how it manipulates data, and then from that, argue that it did things the right way, right? Whatever it is, the output I get, that is the largest number, that type of thing. Let's see. I think I forgot to replace my example here for the first one. Yeah, that's still the old one for the previous slide. So I'll just make up an example quick there. So for example, I had a proof of correctness. So imagine, right? You have an algorithm, right, that needs to find the maximum number in an array, right? Your proof of correctness would basically show that when I run this on any input, the number that I get out is indeed larger than everything else. Okay, which seems like a trivial thing, right? Your algorithm is sort of going to brute force it, right? You're going to basically try every index against every other index, try and see what's largest. But your proof there would basically say, okay, yeah, whatever comes out, for sure you've had the opportunity to compare it to everybody else, therefore it has to be the largest one. Okay, that's a really simple example. The other example there, right? So again, this is the finding a path, from some place to some other place, so from home to school. Their proof of correctness would basically have to argue that if a path exists in the input data, the algorithm can find it, right? And then if there isn't any path in the input data, right? If there isn't a way for me to get to school, then I can't find it. That's actually a really, really hard one, because you can imagine, right? If I want to find a path from home to school, I have a million different options for how I can get there, right? So your proof for that would be really complicated, right? To basically assert that if there is a path, I always find one, right? Given that I have to basically, say that every single option is tried, right? That's kind of a difficult thing to argue. But again, you can do it. So yeah, so the proof of correctness, right, is just showing that our algorithm is doing what it's supposed to be doing. All right. So really quick, right, this is a proof of correctness for swim. This is our example, right? So we want to show that basically swim is correct. And basically what that means is that, once we run swim, right, we get back a valid heap, right, that is complete, right? We basically fix one little position there. And here, right, I've just done really quick to show this is, well, the bottom basically is me substituting in some stuff. So I got rid of my formulas here because I was like, well, the formulas kind of slow me down. I have to remember what does that math formula look like to jump around the array. So I just substituted in there kind of the keyword parent. That's something you'll kind of see a lot of times. People will be like, oh, okay, just say, the parent of K represents the parent of K, right? That way I don't have to use the formula. I can just use words. So yeah. So for this algorithm, right, we basically need to show, right, so for swim, right, if we want to show that it is correct, we need to show that it, always produces a complete tree, and then also produces a tree where the things are in the valid order. The complete tree thing is easy to see. You just look at it and you say, oh, the only thing you ever do is swap nodes. If you're just swapping nodes, you can't ever change the structure of the tree. So for sure, it's going to be complete. Seeing that you don't break the tree structure is a little bit more complicated. The full proof is on the left-hand side. The basic idea, right, is that if you're looking at a node and it's out of order, right, you're looking at the parent, you swap with the parent. If you swap with the parent, you're going to still be with, you're still going to be basically, well, okay. So if you're, say, a misordered node, right, so let's say we have this here, right, so let's say this is K. This is two other nodes, so 10 and 5. The observation basically is that if I'm the only one out of order, I know basically that this parent over here is greater than this child on the other side, right? The other one, right? My sibling, right? So then if I replace myself with them, that heap rule still holds, right? So my K is going to be larger than 5, right? So I know basically K is larger than 5. I know that fact. And I also know K greater than 10, right? So if I rewrite it to look like K up here, 10 down here, 5 over here, it's still a valid heap, right? So left side is just kind of the mathematical argument to show that, to say, okay, these properties will still hold if I perform this operation, right? So yeah. and then it repeats, right? So basically every time, what you're showing is that basically every time this loop runs, the only case it does something is the case where there's work to do, and whenever we do work, we always make the situation better, right? We always basically kind of move upward, right, and kind of get it to be, the final node. And once it's the final node on top, well, there's nobody above me, so obviously the heap rule holds for my node, right? And if we just repeat that again and again and again, basically either we stop because we're done, or we're at the end, or we do a little work where we exchange it and it's still complete and it's still heap ordered. Okay, so put that together. We show that swim always works properly. Okay, that was fast. Questions, comments, concerns, complaints, critiques. Anything you guys have on that? I just have a few more slides I want to wrap up and then call it a day. Okay. And there's kind of extended versions of this, right, that you can go look at. Okay, actually not for this one, for the bigger proof, right, for the priority queue one. There's going to be a bigger, the write-up basically is bigger than what we have in the slide, so there's more information there. Okay. So real quick, let's try applying a proof of correctness to our actual algorithm. It's not going to be too bad because it kind of relies on the fact that swim and sync work. So you want to basically, make sure that we are, processing the heap with at most one node that's out of order, and then, making sure it gets fixed and, the thing's a complete tree at all times, right? That's our metric one. So we want to show that that's met. This we actually do by cases. So we actually can say, okay, maybe the tree has something that's out of order that I need to maintain, and then and maybe it doesn't, right? In the case that it doesn't have what we need to update, then everything's good, right? Because if you think about it, this step one here, right? All this stuff, right? It basically is checking to see, is there work to do, right? And if there's not work to do, well, then of course it's correct, right? I'm not going to break anything in the tree because I haven't changed anything in the tree. And if I can't find a thing I'm told to update, well, then it also means that there's nothing out of order for me to change, right? So in the first case, right? So I say basically, assume that that there's nothing to update, right? All is well, right? I don't break the tree. I don't make enough changes to break it. Versus right over here for case two, we're saying, okay, maybe there is something in the tree, right, that has the stuff that, it needs to be changed. What can I do? Well, I'm basically going to defer here, right, to sink or swim, right? So I check to see, is the element that I'm looking at, is that bigger or is that smaller than what I, expect to be there, right? And depending on that, I defer to sink or swim. Well, sink and swim are already kind of independent algorithms. I know that they, work, right? Or I know that they don't work, right? Fortunately, we have the proof on the previous slide, so it's like, yeah, I can see that they work. So we already know those facts, right? We can say, okay, we're just deferring to those other ones. Those are going to be fine either way. And then I realize, right, that those particular algorithms, right, the swim and the swim and sink, right? Well, basically, if I'm calling those, they're either going to, look at the node and do nothing, or they're going to look at the node and put it in the proper position, right? So in that case, basically, life is good. I get, again, a complete tree. I get one where everything is valid, right? So I kind of build on top of what I already have in order to get out, my final answer. Okay, and I think I'll answer that question up top really quick. So some of this is actually only needed because we have what we call a mutable data type. If, for example, my tree wasn't really mutable, I don't need to worry about changing it, right? So I won't even need to have the kind of the step one discussion of like, oh, everything is fine. You never change anything anyway, so you can't possibly break in and make it not a heap, right? So some of this only comes from the fact that we have this kind of mutable state where we're updating data over time, right? If nothing can change, right, if it's immutable, then everything's just going to be fine. Okay. Let me think. Have any other comments here? I think we should be good. All right. I think we have 2 more slides, and then we'll call it a day. I was really trying to get you guys out of here early. I don't know how much early we'll be. Yeah. So last thing, which is actually going to be familiar, which is why hopefully we can all look at it and agree that it kind of makes sense to us, is proof for efficiency, right? So we said we want it to be an efficient algorithm, and we want to measure efficiency as in the number of lines run. How do we do that, right? Well, we're going to have to look at the code and basically write a big O expression for it, okay? The problem, of course, is that we don't really know, how fast a solution could be, right? Because the problem is, right, is that we don't have a goal, right? We're not told, make it run O of n time, and we're just told make it efficient, right? And so that kind of implies making it as efficient as possible, which relates to the idea of a lower bound proof that we saw back when we talked about merge sort. So final slide here. And I think I may have gone through a couple slides that aren't in the file on Canvas. I got to update it on there. So our final note here is basically about our full performance, right? So this is kind of a, it's us doing Big O, right? Big O is, kind of a familiar thing to us by now, right? We kind of look at this and basically figure out how much work needs to happen, right? So like this line over here, that runs once, right? All this stuff over here runs n times. This over here runs once or twice. I'll just put it as once though, because we're doing Big O. Big O is like, worst case. And this stuff over here, right? Well, this over here, right, really costs log n amount of work, because when we go to do sink and swim, both those are algorithms that take log n time, because they have to move up or down the tree, and I don't know how big the tree is, right? I mean, the tree may be bigger, it may be smaller, it's going to have high log n, right? So yeah, so these are my different parts of my algorithm, right? And so initially, I start off here by basically doing what it is that I typically do in Big O, right? So I look at these, I'm like, okay, this is Big O of n, Big O of log n. Well, in the end, right, I know that O of n is more expensive than log n. So this whole thing here is O of n, right? O of n, where it's number of lines run, LOC run, I should say, lines of code run. That's our metric here. Okay, so for the stuff we've done up until now, basically this is where you end. You say, okay, this is the Big O analysis for it, I'm good to go. The problem is that our question prompt doesn't say build a linear time algorithm, it just says an efficient algorithm. So we need to somehow argue that our algorithm is the fastest one that could be built. And the way you do that here is actually a little bit, so it's a little bit tricky. Like I said, there's a longer write-up about it, but here's the basic idea. If I'm looking at a tree, right, so I'm looking at, okay, I should say a heap, right, so I'm looking at a heap, right, my heap looks something like this. I initially don't know where exactly the node that's out of order is. And I have no information about it because the whole point is it's out of order. So I don't get any knowledge, right, about is it going to be near the top or is it going to be near the bottom? Is it going to be left or is it going to be right? The whole point of the algorithm is that I don't know anything about the thing that I'm being asked to update. It could be anywhere in my tree. Okay, that's my first observation, right? So it's fair game to be anywhere because it's already been, we've already admitted the fact that it could be any value. So it could be anywhere in our tree. So that's one fact, right? And so then the problem is that implies we need to find out where it's at. Now, again, because we don't know where it's at, we don't have any good starting place. Any starting place is as good as any other, so let's start at 0, right? Start at 0 and basically have to search. And if we're looking at a particular node, right, we might try to narrow down our search by going left or going right or going up or going down. The problem is that if I'm looking at any particular node, right, I have 2 children I could go move towards. I simply have no evidence to guide me either way. Do I go to the left child or do I go to the right child? I can't, make a beeline for the node that I'm replacing, right? So if I'm trying to change this one over here, right, and I'm starting over here, I don't know that I'm supposed to make go to the left twice. I don't know that. I have no knowledge of how to get from my starting position to where I actually want to go, right? I don't know how to get there. And because of that, I can't in any way narrow down my search to be just like one path in that tree, right? Because the way you get the log n thing is by only going through one path, right? Because that's the height of the tree. I don't have any way to decide, do I go left or do I go right? Therefore, the only thing I have to do is just go brute force one element at a time, right? So there's no way to get a log solution defining that target node. You have to span that O of n time in order to find out where it's at, right? So no log time solution, linear time is required. Therefore, our linear time algorithm above is the fastest one possible, is the most efficient one to update the contents of a priority queue. All right, so that's our proof of efficiency. So we know that it works right. We know it's as fast as it can be built. We should be good to go. So that basically completes our proof and design, right, for this algorithm, right? Now we have a valid and working, algorithm for updating our priority queue.